I'm guessing that you've had the experience of rubbing a balloon against your hair, and then when you take the balloon away from your hair sticks up. And if you haven't had that experience, you might think about trying to lead a more rich and fun life. But I'm guessing most of y'all have done that. And you've had a sense that it had something to do with the balloon or your hair somehow exchanging charge, or now one's going to be more positive or negative than the other, and so now they are somehow attracted. And if you are thinking of those things, you are generally right. What you just experienced after you rubbed the balloon on your head and then your hair is now attracted to the balloon, that's actually called the triboelectric effect. Let me write that down. Triboelectric effect. And human beings have been observing this for a long, long time. It wasn't necessarily with balloons at birthday parties or whatever. It's with other things. They rub a silk cloth on a piece of glass, and then they'll see that there's some type of attraction, or they might see that if they do that enough, one of the objects might discharge when it touches another object. People have observed things like lightning, where it looks like there's some type of a buildup and some type of a potential, and then all of a sudden it discharges, and you have this lightning and then this thunder, blast, a sound that happens to it. So this is something that humans have observed for a long, long time. And scientists, or people with I guess you could say a scientific mind, have been trying to understand it for a long, long time and trying to come up with a framework for what exactly is happening. Well, lucky for us, we now have a framework for it that explains it quite well. And that framework for what is going on with this triboelectric effect is the framework around charge. Is the framework that we now have around charge. And this tells us, this way of looking at the world says, look, there are some things that just have a property called charge. Some things have a positive charge. Some things have a positive charge, and it's somewhat an arbitrary name. We just happen to call it positive. And some things have what we say is an opposite charge, or a negative charge. A negative charge. We could have called this the magenta charge and this the green charge. We could have called this the hippopotamus charge and this the ostrich charge. And we could have said that hippopotami, I believe, plural for hippopotamus, they're always attracted to ostriches, but they always repel other hippopotami. And likewise, the like charges repel or like hippo. Well, you get the general idea. But I'll stick to the words that people are used to using. And so if we say something has a charge, say a positive charge, and something else has a negative charge, then in our framework that we're setting up, these two things are going to attract. So opposite charges are going to attract, while like charges are going to repel. So if you have a positive charge and you have a positive charge, these things are going to accelerate away from each other. And that's not just true for positive, that's also true for negative and negative. These two things are going to repel because they are like charges. Now, it's very interesting to think about this because we're so used to thinking in terms of charge, even, if you, especially in kind of the world of electricity, you have the positive and negative terminal. You think about charging up your phone or whatever else, that it just seems like, okay, we completely, charge is just something that is fundamental about the universe. And that's true that's true. But you really have to appreciate that these are arbitrary words, and they're really just to describe a property that we have observed in the world. And if you go down to the atomic level, we can get to a fundamental level of where the charge is happening. But once again, these are really models for our brain to describe. These are frameworks and models for our brain to be able to predict and describe what we observe in the world. But if we run with this model, we can imagine at the atomic scale, the nuclei of atoms are composed of protons and neutrons. So you have some protons, and then you have some neutrons. I'll do two of each. You have some neutrons. And based on this framework, protons have a positive charge. Protons have a positive charge. Now, once again, this convention of calling them positive and putting a plus on it, it's not like protons have a little plus sign tattooed onto them somehow. We could have said they have a red charge, or we could have even said we wouldn't have had to even use the word charge. This is just the convention that we have decided to use. And so we say protons have positive charge, and then or kind of buzzing around the nucleus of an atom, you often, or usually, or I can say often have electrons. And electrons have a lot less mass. And mass is another interesting thing. We associate mass as just, oh, this is just something that we get. We understand it in our everyday life. But even mass, this is just a property of objects. It's just a property of matter. And we feel like we understand it because on our scales, we understand notions of things like weight and volume, but even mass can get quite exotic. But anyway, the whole point of this video is not to talk about mass, it's to talk about charge. But all of these things that we talk about in physics, these are just properties that help us deal with these notions, these behaviors in different frameworks. But anyway, let's get back to this little atom that I was constructing. So this atom, let's say it has 2 electrons, and obviously this is not drawn to scale. And each of these electrons have a negative charge, and they're kind of jumping around here, buzzing around this nucleus of this atom. And the reason why this model, even going down to the atomic scale and thinking in protons and electrons is interesting, is that it allows us to start explaining what is happening in the triboelectric effect. What is happening in the triboelectric effect is when you rub that balloon on your hair, because of the property of the balloon, the material of the balloon and the materials of your hair, when they come in contact and they rub, the balloon is grabbing electrons from your hair. So the balloon is grabbing electrons from your hair, and so it is getting more negatively charged. It is getting more negatively charged, and then your hair is getting more positively charged, or it's essentially just lost these electrons. And so when you put the balloon now close to your hair, remember, like charges repel each other. So the electrons in your hair try to move away from these other electrons. The negative charge tries to move away from the negative charge. And I guess you could say that the tips of your hair will then become more positive, and they will be attracted to the balloon. So we can think about what's happening in terms of transfer of electrons, and that's exactly what's happening. And so when you think that way, it's like, okay, well, we are scientists. This is a nice model. We can start to think about what's happening here. This model actually explains a whole ton of behavior that we've observed in the universe, including things like lightning and whatever else, and the static shock that you get when you might touch a doorknob after rubbing your shoes along the carpet. But we like to quantify things, so we can start seeing how much they repel or how much they attract each other. And so the fundamental unit of charge, or one of the fundamental units of charge, or I guess you could say the elementary unit of charge, is defined in terms of the charge of a proton or an electron. So the fundamental, or I guess you could say the elementary unit of charge, is denoted by the letter E, and this is the charge of a proton. And this is E for elementary. Charge of proton. And the charge of an electron, even though an electron has a much smaller mass than a proton, most of the mass of an atom is from the protons and the neutrons. So an electron has a much smaller mass than the protons and the neutrons, but it has the same but opposite charge as a proton. So sometimes the convention is to write negative E, or maybe even negative 1e sometimes, depending on whether you view this as a kind of the actual charge or whether you view this as a unit. But here we'll view it as the actual charge. You could view negative e as the charge of an electron. And something that has no charge, like a neutron, we say they're neutral. And actually that is why they are called neutrons, because they are neutral. They don't have charge. So that right over there, is a neutron. Now, when we start to get on kind of a larger scale, not on a subatomic scale anymore, talking about electrons and protons, the unit of charge, or in general, the unit of charge that we typically use is the coulomb. Coulomb. It's named for Charles Augustin de Coulomb. So if we're talking about the guy, and he was an 18th century French physicist, we would use capital C. But if we're talking about the units, we would use lowercase c, the coulomb. And the coulomb is defined, so 1 coulomb, let me write it right over here. 1 coulomb, and it's used the abbreviation uppercase C, is equal, or I'll say approximately equal to, we're going to round here, it's approximately equal to 6.24 times 10 to the 18th E. Or you could say, in magnitude-wise, it's equal to the charge of 6.24 times 10 to the 18th protons. Or magnitude-wise, it would be the opposite if you're talking about electrons. It would be 6.24 times 10 to the 18th electrons. Now, if you want to go the other way around, what is the charge of the magnitude of the charge of, say, a proton in terms of coulombs? Well, you would just take the inverse of this. So you could say that E is approximately equal to the inverse of this, which is 1.60, I guess you could say the reciprocal of this, 1.60 times 10 to the negative 19 times 10 to the negative 19 coulombs. So hopefully this gives you an appreciation for, I guess at a base level, what charge is. And in some ways, it's like, it's this everyday thing. You're used to it. We're used to dealing with electricity, and we'll talk much more about that in depth. But on some levels, it is this, it's this thing, one of the mysteries of the universe. How do these two particles know to attract each other? It looks like they're at a distance. How do they immediately exert a force on each other? How do these particles know immediately to repel each other? It's not like they have a wire connecting them that they're communicating somehow. Or well, I guess once you get to quantum mechanical, an argument can be made that they are communicating somehow. But in our everyday kind of logical sense, it's like, well, at a distance, how do these things actually know to repel or attract? And what is this charge anyway? We've put all these names around it, but to kind of help us think about it and have a framework and predict what will happen. But do we really know what this charge thing is? So on one level, it's kind of plain and mundane, and it deals with balloons and hair. But on another level, it's this deep thing about this universe. It's a deep property of matter that we can manipulate and we can predict, but it is still this very fundamental and somewhat mysterious thing.